Hello students, this is Mr. Ezra. Today we are going to talk about graphing exponential functions. We're going to look at three different parts of graphing exponential functions. We're going to look at some characteristics of exponential functions. We're going to look at transformations of exponential functions from the parent function. And we're also going to actually look at how to get them onto a graph so that we can see what they look like. So before we jump into characteristics or transformations or graphing, I want to talk really briefly about exponential growth versus exponential decay. For our purposes, we're going to consider exponential growth to be growth that is very slow at first, and then over time it begins to increase and grow much faster. Okay, we can actually look at a function or part of a function and know whether or not the function is going to be classified as exponential growth or decay. I mean, certainly if you had the function, you could just graph it and see if it looks like growth. If you focus on the base of the exponent in the function, that base tells you whether or not you have exponential growth or decay, or something else, I guess. So first, for exponential growth, you have to have an x in the exponent. There has to be a variable in the exponent. And you want to look at the base. If that base is greater than 1, then it's going to be considered exponential growth. Or if you have a negative exponent, for example, if whatever exponent is up here had a negative in front, that would cause the b to flip to its reciprocal. And if that reciprocal is greater than 1, then it's going to be considered exponential growth. So for example, if I had y equals 5 to the x, since 5 is the base and it's greater than 1, it's growth. But if I had 1/5 raised to the negative x, that negative would cause the 1/5 to become its reciprocal. So 1/5 to the negative is actually 5, 5 to the x in this case. And 5 is greater than 1, so it would be growth. So one of these two things happens. You look at your base, you know it's growth. Decay, on the other hand, happens when you look at the base of this exponential function and you notice that b is a fraction that is somewhere between 0 and 1. If you have a negative in the exponent, that would of course cause the base to flip to its reciprocal, and if that reciprocal is between 0 and 1, then it would be considered exponential decay. So you don't want to just look at the base, but you want to look at the base and the sign in your exponent. If there's no negative sign in the exponent in front of your x, then you're good to go. Just you look at b, is it a fraction or is it a number bigger than 1? It can be a fraction and still be bigger than 1. So if it's bigger than 1, it's growth. If it's between 0 and 1, it's decay. But if you have a negative in the exponent, then you have to think about whether the reciprocal is larger than 1 or between 0 and 1. So let's look at a few of these and see whether we think they are exponential growth or decay. 2/3 is a fraction between 0 and 1, so you should classify that as decay. That's simple, right? 5/4 is a fraction, yes, but it's a fraction that is 1 1/4 or 1.25. That's larger than 1, greater than 1, so that would be classified as exponential growth. And 6 is the base of number 3. It is larger than 1, so that is also going to be exponential growth. So it's that simple. Find the base, look at it, see whether it is growth or decay. Let's look at a few more examples. Now here I've got another number in here, but to decide for growth or decay, I don't need to look at the first part, which we call A. I want to look at the base. This base is 1/3. 1/3 is between 0 and 1, so it would be decay. Now up until this point, if we look at our examples, all of our x values have been positive, so we haven't had to think about a negative exponent and its impact. But in number 5, we do have a negative exponent. So while 3/4 is a number between 0 and 1, that negative forces it to be 4/3. And 4/3 is an improper fraction. That means it's larger than 1, greater than 1. So in this case, since the reciprocal is greater than 1, it is going to be considered to be growth. And finally, ignore the 2. We have no negative in the exponent. 0.15 is between 0 and 1, so that's going to be decay. So this can be pretty simple for you to make this decision of whether or not it is growth or decay. Let's talk about some transformations. Certainly, if A is positive or negative, that would cause, let's see, a negative A would be a reflection across the x-axis. Okay, and the larger A, I mean, A can be like a vertical stretch or a shrink, just like it always has been. I want to focus in, though, on the h and k part of this function, and it might make more sense once we get to some examples. But basically, I want you to know that shifts left and right are going to happen with h, which means they're going to be added or subtracted inside the exponent. And shifts up or down are going to be at the end. This should be kind of similar for you in functions that we've studied in the past. The part at the end was the up or down, and the part in the parentheses was the left or right. In this case, we're going to consider that exponent to be kind of like being in the parentheses, like if you want to think about those other functions that we've looked at. So in number 7 here, this plus 2 is at the end. That is going to be a shift up or down, and it's going to be exactly the way that we think it should be, right? Plus 2 is up 2, a shift up 2, right? For number 8, we have 2 to the x minus 5. The minus 5 is at the very end of the function. It's going to be up or down, and since it's minus 5, we're going to consider that to be down 5. Now, the x plus 1 in the exponent of 5 over 3 to the x plus 1 means that this is a shift left or right. This is where you have to be careful, right? Just like the other functions that we've studied. What's going to happen here is what shifts left or right are always going to be the opposite of what they look like in the exponent. So plus 1 is actually not going to be right to the 1, but instead is going to be left 1. So outside of the exponent at the end is going to be up or down, the way that you see it. In the exponent is left or right, and it's the opposite of the sign that you see there. And if you look at the function itself, that x minus h is a clue as to the fact that when you subtract a negative, you actually add. When you subtract a positive, you actually subtract. So that's why subtracting a negative here is actually left. And we've talked before about why these force the function to move left and right on the graph. Let's try a few more examples here. So x minus 3 is in the exponent. That's left or right. Because it's kind of the opposite direction of what it looks like it should be, we're going to go right 3 for this one. Okay. Now, negative at the front is certainly a reflection across the x-axis. That's okay, but I'm not really concerned about those right now. I want to know, is there a shift left or right, or is there a shift up or down? There's no addition or subtraction in the exponent. There's no addition or subtraction at the end. So that means that while there is a reflection across the x-axis because of the negative at the front, there is no shift left or right. There is no shift up or down. Okay. So whereas this function was growing up, now it's going to grow down. Still growth, but it's growing in the opposite direction. And finally, we have 3 times 2 to the x plus 2. I want you to look at this plus 2 and tell me that that is going to be a shift up 2. Okay. This should feel familiar to you if you have been successful with transformations in the past. It should have a kind of a similar feel to you. Now let's talk about some of the characteristics of these types of functions. Because exponential growth functions, although they can be reflected, but the parent functions are either growing or decaying, they either grow or decay forever from left to right. So their domain is all real numbers, or from negative infinity to positive infinity. That will always be the domain unless for some reason you have a word problem that limits the domain based on the context of the problem. The range is going to be limited though. These functions, as we'll see in a minute, have what is called an asymptote. Okay, so either there's an asymptote below the function, and the function is either increasing forever or decreasing above the asymptote, or there is an asymptote, and the growth or decay is happening below the function, right? So with the range, that asymptote is going to kind of decide where we start seeing y values or where we stop seeing y values. And your clue there is just to look at the leading coefficient at the very front of the function. If a, which is going to be the number, not the base, but the number in front of the base, if that is a positive value, then you're going to have a situation where it is above the asymptote, and you would say asymptote up to infinity. Or we'll see in a minute the asymptote is going to be this letter or number k, whatever that turns out to be. So from there to infinity is the range. If a is negative, it reflects across the x-axis, might shift up or down from there, but it's going to reflect down. So it's going to be pointed in a different direction, and we'll have y values below the asymptote, and they'll stop at the asymptote, or they'll approach the asymptote but never quite get there. So we have two possibilities for range, either from the asymptote to infinity, if a is positive, or from negative infinity to the asymptote if a is negative. Let's practice identifying the domain and range. Since the domain is always the same, all real numbers, negative infinity to positive infinity, we're really looking at the range here. The clues that I have about the range are the fact that there is a negative in the front and that it shifts up 4. So when I'm trying to identify the range, I know that it's going to go, the function is going to be below the asymptote because of the negative, and it's going to stop at the asymptote, which is 4. So the range is going to be from negative infinity to 4. It might help you at first to graph this in your graphing calculator to see what the function looks like and to see that the whole function is below the asymptote. In the next example, and by the way, these are not numbered correctly. I just didn't white them out or change them, so I'm just kind of skipping around in numbers. We have a positive 3, so it does not reflect down. We also don't have a shift up or down for that asymptote. So since it's positive, that means that the function is essentially above the asymptote. So for our range, we're going to start at the asymptote and go up forever towards infinity. Now, you might be thinking, well, Mr. Ezra, there's no asymptote here. Well, there is an asymptote. It's just not shifting up or down, so it's going to stay at 0. So our range will be from 0 to infinity because it does not reflect down across the asymptote. It's from the asymptote to infinity. Also notice that the range and domain all get parentheses. There's no brackets here because while our function approaches the asymptote, it never actually reaches the asymptote, or as it gets closer and closer, whether it's above or below, it approaches it, but it doesn't actually ever reach that asymptote. So we can't count the asymptote as a solution. Our next example, we have a positive, so it's above the asymptote. And what asymptote is it above? -1. So we're going to say that the domain is always from negative infinity to positive infinity, but the range is going to be from -1 to infinity. Again, as you're getting used to this, feel free to graph the function and see what it looks like. See if it's above the asymptote or below the asymptote. Speaking of the asymptote, I've already said this, but a line that a graph approaches but will never touch is what we consider to be an asymptote. When you graph it, just like other asymptotes, you need to use a horizontal dashed line, a dashed line, in this case horizontal, to represent the asymptote. And the asymptote is actually pretty easy to identify because it's always that shift up or down. The asymptote of the parent function is 0, or y equals 0, I should say. Well, since this is the shift up or down from 0, it lets us know where the asymptote shifts to. So, in these examples, we have 3 to the x minus 2 plus 4. The asymptote is going to shift up from 0, or y equals 0, to y equals 4. That's simple. In the next example, it's going to be y equals -3. And in the final example, just like last time, just like a minute ago, there is no shift up or down at the end. Because of that, the asymptote is going to stay at y equals 0. which is also known as the x-axis. Notice we don't care if it shifts left or right in the exponent. That does not impact the asymptote. If the asymptote shifts left or right, it's still the same horizontal line. It's only going to move if it's up or down. X-intercepts are going to be considered where the function crosses the x-axis. There are occasions where the function does not cross the x-axis, so it is possible that you may not have an x-intercept. Remember that anytime you want to find an x-intercept, you can do this algebraically by letting y equal 0, and then solve for x. On a graph, if you are able to graph this function, then you'll just look at the graph to see where it crosses the x-axis. The y-intercept is where the function crosses the y-axis, and algebraically you can find a y-intercept by letting x equal 0 and solving for y. If you have a graph handy, you could look at the graph and just see where the graph crosses the y-axis. When we talk about intervals of increase or decrease, these exponential functions are always increasing or always decreasing. So the interval is always from negative infinity to positive infinity, that interval of increase or decrease. It is really your job to just look at the graph to see, is it increasing or decreasing? We know that it's going to be doing that forever, but is it going up from left to right or down from left to right? That's your job to look at the graph and see. I think it might be easier for us to talk about end behavior in the context of some problems, and we're going to look at a few examples here in a minute. But basically for the domain, we're going to say x is going to go forever to the left, and x is going to go forever to the right. In other words, as our function goes to the left, what's happening to the function? What's it approaching? As we go to the right, what's happening? What's the function approaching? This is our basic outline for how we represent end behavior, this notation right here. And we'll have to look at in context what happens here, because it's not just going to be positive and negative infinity. Sometimes it's going to approach the asymptote on the left or the right.